Right, look again. All right, can everyone settle down, find a seat, stop talking, we're going to start. Okay, so today, a little catch up on sort of where we've gotten to so far in the course. We've covered sort of seed, it sort of falls into three blocks. We have sort of the introduction and the statistical component. And then this sort of talking about these broad scale patterns that leads up to terrestrial ecosystems we're going to talk about today. And then from now until the 15th of October, we'll be talking more about nutrient dynamics, energetics in an ecosystem, system functioning, things like that. So today, a little bit of a change, we're sort of going to move down and talk about terrestrial ecosystems. A bit of a change from the syllabus, but it kind of follows on nicely and clearly from what we've been talking about in relation to climate and the physical environment up to now. So when we've been talking, or the last few lectures, I've been saying that, oh, climate's very important, and temperature is very important, and the amount of water that's available is very important. We've talked a bit about why these are important, but in today's lecture, we're going to talk and discuss some of the consequences of it. What happens, what type of an environment do we see in different parts of the globe? And this is as a consequence, as a result of the amount of light availability, the variability in light availability, the amount of water that's available, temperature, things like that. So we know that the planet is heated unequally, the heat is distributed, but we've got parts of the globe that are warmer than others, parts of the globe that receive more rainfall than others. And as a consequence of these, we have parts of the globe that have different biotic community. And this plot here is a figure sort of taken from the textbook, and it's simply a different way of distributing this or visualizing this relationship. On the x-axis, we have mean annual temperature, sort of ranging from 30, the warmest part of the planet, to minus 15. And then on the y-axis, mean annual precipitation. Wetter areas, drier areas, warmer areas, colder areas. And if we take this scale and put all the different types of environments and different types of habitats that we see on the planet and situate them somewhere within this plot, we get a distribution that looks kind of like this. We've got things like tropical rainforests, which are characteristic of the warmest, wettest parts and areas of the planet. Deserts, characteristic of a very warm area but very low rainfall. We can move down into a tundra, an Arctic biome, where we've got low rainfall and also very low temperature. You'll notice that everything sits on this corner of the plot. There's nothing up here. Any ideas why? What's happening up here? We've got very low temperatures and very low or very high amounts of precipitation. We don't see that occurring because that when the air is that cold, it cannot hold water. It cannot hold that moisture. So it can only hold moisture when the air is warm. So by the time this air has cooled here, it's already lost its moisture. So if we have, and we'll see when we talk a bit more about desert environments, when we have very cold areas, there are always very dry areas. So over the course of this lecture, we're going to go through and discuss some of these different biomes. A biome is, I talked a little bit in the last lecture about how we can identify areas, like ecoregions, based on the types of plants that are there, the biotic community that's there. The biomes are the broadest level of those that we can put on, particularly in this lecture, we'll talk about in a terrestrial environment. Things like tropical rainforests, tropical seasonal forests, temperate forests. There will be a lot of variability within these, particularly where soils are involved. So we're talking about an overall general what biome we see in the climate, if we've got a specific climate, but at a more local level, the type of soils we see will also determine the type of plants that exist. We characterize these biomes primarily by the plant species that are there, the type of plant communities that we see that are characteristic of a region. And there's a number of very good reasons that we use these. Primarily, that the plant community that's present will determine, as we saw, the amount of light that gets through, the temperature, the humidity, and a lot of different microclimates. So by understanding or by knowing the plants that are there, that allows us to understand what comes downstream. It allows us to understand the autotrophic levels. The plants constitute the base of nearly all food chains in a terrestrial environment. They're the resource for any herbivores and also decomposers. So plants, and in addition, they constitute the habitat, physical habitat for the majority of other animal species that live in these regions. So for a whole host of ecological reasons, it makes sense to consider the plants as the basis for the food web, the basis for the ecosystem. And if we want to characterize an ecosystem, it therefore makes sense that we should focus on the plant. There's also certain practical reasons for this. It's much if the plants are typically not nocturnal, they don't move around very much. So it's very easy to go to an area, observe what plant species are there, tick them off on the list, and characterize it that way. If you want to know what insect species are there, you have to go and set up a series of traps and experiments, and it takes a lot longer. You may have seasonal distributions in the animal community. Again, that makes it more difficult to characterize an area. The plant species don't change very much over time. So as we go through this, we're going to see a lot of this figure. And a simple goal for this is sort of to demonstrate, okay, well, we know these are the characteristics we're talking about in terms of climate, and this is roughly or broadly where we find them. We're going to start with the first biome of tropical rainforests. So remember here we're talking about areas that are amongst the warmest on the planet, but also receive a lot of rainfall, receive a lot of our high annual precipitation. Now that varies seasonally. We're not, in a little while we'll talk a bit more about the effect of that seasonal variation. But certainly from this plot we're just looking at the main overall annual trend. And here we find the majority of these situated along the equator. We're receiving the most amount of direct solar radiation. And they're also, as we discussed when we talk about the aquatic environment, the role of moisture, the role of water, along here we've got massive amounts of evaporation. That air, that moisture-rich air is rising. It's warm, heated air, it's rising. Remember we've talked about that feral cell or cell cycle. And as that's rising, the water is condensing and falling as precipitation. So that's why we have these traits. We have this high temperature and also very high rainfall. This results in extremely rich, productive, and diverse habitat. They're characterized by a broad diversity of plants. Once we have a broad diversity of plants and a rich, not only taxonomic diversity, but actual biodiversity with lots of different plants filling different niches. We then automatically get a great functional diversity in consumer species, adapted to fill each of those niches. There's the tropical rainforests are characterized by stable annual temperature. Mean temperature sort of around about 25 degrees, varies little through the year, but large seasonal variability in precipitation, characterized by a wet season and a dry season. Temperature remains broadly similar throughout. The plant or the tree community is dominated by large, broadleaf trees with many, many different epiphytes. Remember, we've talked about these epiphytes, which are plants which live on other plants. And this is an adaptation, again, to allow them to get at sunlight. Because we've got this big, dense canopy layer in the forest. Light is extremely limited. So there's a lot of adaptations within the plant community to try and access light. The soils in the most tropical rainforests are extremely poor quality. There's a lot of productivity, there's a lot of biomass and biodiversity, but it's all happening above ground layer. The rates of decomposition are so fast because it's such a warm and humid environment that the nutrients, by the time they reach the soil, are being reabsorbed and being cycled back up by different decomposer communities, different faunal communities, and results in very poor quality soils. There's very low amounts of nutrients in the soils. They're also characterized by extremely high rates of leaching. As we move slightly north away from the climate or away from the equator, we move into what are termed as seasonal rainforests. And here we're in areas that are characterized by a longer dry season. And the forests here have adapted to that. Quite often there's hardwood deciduous forests that will drop their leaves during summer. And this is where things like these areas were intensively forested, like a lot of hardwoods, things like mahoganies that are used for furniture, were taken from this region. We can then continue to move north, moving away from the tropics and moving up into the savannas and the grasslands. So here we see that we're still in a wet or still in a very warm area, but an area with slightly lower rainfall. And this is, we've moved away from that sort of peak zone of evaporation. We've moved away from that area where it's characterized by daily rainfall events. And here we're in an area where the majority of the plant material, the plants are shrubs and grasses, but some tree species still exist. A lot of the system here is characterized by regular burning. So we've got a really long dry season. And during that dry season, there's a very, very high risk of fire, forest fire, land fire. So a lot of the plant species are adapted, their life cycles are adapted to fire. A lot of the tree species will be adapted to be able to burn and regenerate. These areas are also characteristic of the remaining large herbivores and large grazers that we see on the planet. So the sort of charismatic African plain. As we move slightly further north again, we move into what are termed as the grasslands. And here, plot? No. So we're sort of tucking up here in the US, sort of a Eurasian steppe. And here we're moved into an area which is slightly drier, or still remains slightly dry, and slightly cooler temperatures. Fewer tree species. More sort of what we would see as a sort of characteristic or a typical seasonal environment. We tend to have some fire events, but they're not as frequent. The plant community is dominated by grasses, because the majority of, or at least in terms of their biomass, the majority of plants that are there are different species of grasses. Because of the type of production and productivity we see here, with grasses growing, decomposing, growing, decomposing, growing, decomposing, over time they build up very deep, fertile soils that are heavily rooted due to the characteristics of the species that are there. There's variation within this as well, either at a broad or a continental scale. If we look across North America, North American prairies, if we travel from east to west, we're working along a climate gradient, not so much in terms of temperature, but in relation to precipitation. On the east side, we've got more rainfall than we see as we move out to the west. And the type of grass species that naturally occur in these regions, that we would naturally see in these regions, reflect that. The species on the east side are termed as tall grass species. As we move further west, we move into more short grass species, or areas characterized by short grasses. And this whole region was home to large grazers and burrowing grazers, which is characteristic image or iconic images of bison roaming the plain. When people arrived, or at least when Europeans arrived here and started colonizing North America, we have taken this sort of natural characteristics and used it to our advantage, or adapted our land use to the type of environment we see. So if we sort of replace that initial map with a more current map, and we see what's happening on the tall grass prairies, are now the areas that are characterized by the most intensive agriculture. Areas that are characterized by large maize, or further north, by large wheat or intensive wheat agriculture. We're using the characteristics of the environment, or adapting what we're doing with the environment to the characteristics of the environment. This is an area that naturally would be well suited to deep and rich growth of plants, or grasses growth of grasses. We're using this as our bread bowl, our bread basket for intensive agriculture. As you move further west, onto the plains, or the short grass prairies, areas that were traditionally or characteristically home to those sort of large herds of grazing herbivores, are now the areas that we use for intensive agriculture, for intensive livestock agriculture. Using the same, adapting our techniques to the environment that's there. All of this ultimately driven from the ground up by the climate, by the temperature regimes, by the relative amounts of precipitation. As we go a bit further, we move into the deserts. So here we're talking about areas that are characterized by extremely low rainfall. They can exist along a temperature gradient, but always having very, very low rainfall, typically less than 15, 20, 30 millimeters per year. There's a great diversity from what we term as, what we would characterize as sort of hot deserts from dune systems in Saudi Arabia, temperate deserts, which exist in the rain shadows. So if we look along here, the US deserts, those sort of North American deserts that exist in the rain shadow of the Rockies. And then finally, things like polar or alpine deserts, which are characteristic of very high latitude regions or high mountainous regions. So there's a great diversity in that in terms of the temperature, but each characterized by extremely low rainfall for a variety of different reasons. And because of that rainfall, the fauna communities and the faunal communities have adapted to that type of environment. Typically, we're in an area with extremely poorly developed soils. Take, for example, this environment, we'll compare that to the images we showed a little while previously of those rich grasslands, where the additional amount of precipitation, the additional moisture in the environment facilitates additional plant growth. As those plants grow, they die, decompose, all that resource, those nutrients get cycled back into the soil. Here, we've got far lower amounts, or far lower plant biomass, far lower grass or any biotic material. So there's less amount, or there's less nutrients produced every year. Less of that is able to get reintegrated and reincorporated into the soil. So the soils are poor quality soils. If we've got poor quality soil and low amounts of water, it results in a system where productivity is very low. So it gets into a cyclical event where productivity is low, reduces the amount of biomass, reduces the amount of biotic material getting reintegrated into the soil. This leads to extremely sparse environments where species need to be adapted to, or species are adapted to, unique characteristics of that environment. And quite often what we'll see is that these environments, or desert environments, are almost barren for a year, either through an annual cycle where the wet season is restricted to a few short months, or potentially over multi-annual cycles. And the species there need to be adapted to that. And there's two different routes. They can either be, or we term these different strategies as evaders or resistors. An evader strategy is essentially any plant or animal that can keep itself isolated or insulated from the drought or from the extreme heat until a rainfall event occurs. The alternative is a resistor, is species which have adapted to being able to withstand that heat and to maintain their growth and maintain productivity throughout, even when we see that heat. This is an example of a spadefoot toad. And spadefoot toads live the majority of their life buried underground. They're a desert amphibian. They'll stay buried underground, isolated or insulated from the extreme heat. They still have some moisture available to them. When there is a rainfall event, the soils become waterlogged. Cues activity in the frogs. They move out of the soils, find mates, reproduce. That whole activity occurs during a very, very brief period, and then return to the soil. So that by having this strategy, they can insulate themselves or isolate themselves from the most extreme periods in the environment. But when the environment is suitable, they can move and reproduce. The alternative, and a nice example of an alternative, occurs, or we see it within the plant community. And here are wonderful images of desert annuals. And these are plants which are evident if you walk across here we can see these shrubs, and these plants are visible. They are active, they're photosynthesizing throughout the year. But they have timed their peak activity to rainfall events. And that's why we see these spring blooms or blooms of desert flowers associated with rainfall events, so that whenever we get those brief wet periods. There's also particular activity, we talked a bit about this in a previous lecture, about canned photosynthesis. And again, it's an adaptation of drought resistance. It's a method by which they can continue to photosynthesize and continue to grow despite living in a highly arid environment. So, to quick recap, what we see in a lot of cactus species is during nighttime. So when they photosynthesize, a typical plant, C3 plant, when it photosynthesizes, it needs to have its stomata open to take in CO2. When the stomata are open, it's losing moisture. So in a desert environment, or a very arid environment, certainly a plant that is going to exist and continue to photosynthesize year round, that's a very poor strategy and will be very quickly selected against. Or anything which doesn't have that strategy will have a fitness advantage in its ability to maintain water. Canned photosynthesis is where the plants can open their stomata at nighttime, obtain CO2, store that CO2 as an organic acid within their tissues. During the daytime, close their stomata and use up that CO2 and that acid to photosynthesize. And this activity is what allows things like cactus to, despite being a photosynthetically active plant in a desert, to maintain a large reserve of water, to maintain large amounts of moisture within the tissue. Because during the daytime, they can keep the stomata closed, but continue to photosynthesize. Moving on from deserts into temperate shrublands or chaparral. And again, here we're still relatively low rainfall, but just enough rainfall to allow a diverse plant community. Just enough to allow multiple different types of species and species with different types of activities to flourish. So this type of environment gives rise to what we class as like a typical Mediterranean climate. Hot, dry summers, cool, damp winters. But because of the hot, dry summer, these are areas which are characterized by fire, by seasonal fires, so in late summer. There's enough plant material, there's enough fuel there for a large fire. By the end of the summer, these areas are extremely dry, like a tinderbox ready to go. these are also areas where people like to live. The Mediterranean is one of the most densely populated areas in Europe, one of the most densely populated areas in the old world. In the New World, places like California or the coasts of South America are characterized with this type of environment. It's an environment that people like to live in, so they're quite heavily populated. And it leads to a collision. Like when we talked about the agriculture on the plains, where humans have, our activity is determined by the environment. We're using the characteristics of the environment. Here, the same thing is happening, but we're becoming in conflict with the characteristics of the environment because we're trying to build residential zones and places where we want to live in a habitat that naturally is exposed to fires on a semi-annual basis. So this results in every year we hear about forest fires, particularly on the west coast of places in the US and the big city. And a lot of what's happening is these are areas which are naturally would be burning anyway, but we're putting human populations in those areas. And it's a conflict. As we move sort of further north, we see that we're sort of staying in this temperate temperature range, sort of mean annual temperatures between predominantly sort of 10 to 15 degrees, but anywhere above freezing and up to maybe even 20 degrees. But the amount of moisture is increased. And when we get more moisture in the soil and more moisture in the environment, that allows plants to grow larger. We talked a bit when we talked about the gravity and the various factors around life in a terrestrial environment. And water was crucial. And when there's a sufficient amount of water and more water in the soil, it allows plants to grow bigger. It takes away, water stops being a limiting resource. So plants are able to get more nutrients. These plants are able to build bigger tissues, which means they're able to grow larger. So this is where we start to see, we've moved back into forest communities. We sort of moved from that tropical forest down into a desert, grassland, shrubland, and we're moving back into a forest zone as we move back up in the amount of precipitation we see. So here we're characterized, areas which are characterized by a lot more moisture. And initially, we move into these deciduous, broadleaf deciduous forests. Some evergreen trees are dispersed, but there's enough, in this situation, or in this zone, the winter is short enough that it's beneficial, or it allows, a deciduous strategy is the most beneficial, the best adapted to those conditions. So if we move to somewhere like Ireland, the west coast of Europe, where, like we saw in the lectures on climate, winters are 2, 3, 5 degrees, a lot of rainfall, very little snowfall. By the time we're into February, the air is getting warmer again. We've moved into spring. Short winter, it's beneficial. There's a deciduous strategy is the best adaptation for a tree. So we see a lot more deciduous forests. A lot of this diversity, most of this diversity, exists on the southern range of these. And as we move further north, we're moving, as we'll see in subsequent slides, we're moving into a more inhospitable regime, or inhospitable zone, at least for those deciduous plants. Again, this is an area or a type of environment that humans have had a massive impact on, because it's an area where human population growth occurred in Northern Europe, and as people moved into, as Europeans moved into North America, this type of habitat was a very valuable resource. So there was massive deforestation, initially to get the wood for structure, for buildings, and then to reuse that land for agriculture. So we've lost, certainly in Europe, and it's far more apparent there than when we move over here, we've lost vast swathes of this type of habitat to agricultural land. Well, that is slowly starting to recover now as people sort of identify these areas, try and protect and conserve them. As we move a bit further north again, we move into what we term as the boreal forests, or the taiga. And this is an area that is receives somewhat slightly less moisture, but it's a bit colder. So we've moved from areas that are ideally suited to a lush, rich, deciduous forest, where we've got a short winter, through to a evergreen forest or coniferous forest. And here the winters are longer. Let's flip that on its head and say the summers are shorter. So the adaptation of the fitness advantage of being a deciduous tree is reduced because your growth period is confined, is restricted to a shorter window. Whereas the evergreen or coniferous trees, which can continue to grow all year round, have an advantage, grow slower, but grow all year round, have an advantage. In New Brunswick, we sort of sit in a mixed zone between deciduous forests from here south and boreal or coniferous forests from here north. The soils are, in this region, the soils are organic, or can contain a lot of nutrients because they're organic rich. We're in an area with very high biomass, a large amount of forest, understory layers, large amounts of different decomposers, consumers existing within this environment. So there's a lot of organic material here. A lot of that is building up and getting into the soils. But particularly when we move into areas with a lot of coniferous forests, the soils are extremely acidic, or relatively, or quite acidic. As we saw when we talked about soils, and when we get an acidic soil, those nutrients, due to the cation exchange, the ion exchange, are not available to the plants. They're getting absorbed, they're getting pulled into the water and leach out very, very rapidly. And they're less of them, or they're less readily available to the plants. So despite there being a lot of material, the soils are quite infertile. But certainly as we start to move from here further north. Again, we can see how these areas are impacted by human activity. And certainly living in New Brunswick, we can see how exploitation for timber, pulpwood, certainly in the form of clear cuts, we can see the impact that has on a forest environment. If we look at the diversity of other plant species, the biomass of consumer species, are all lower once we've clear cut that forest, even if it has time to regenerate. And that's one of the reasons that there's a lot of movement now to identify new harvest strategies and new management practices, which can try and mimic the natural disturbance that we see in these environments. So there are natural disturbances such as fires, such as outbreaks of spruce woodworm, that will knock out isolated chunks of forest. And we're trying to, or there are movements to try and find ways that we can adapt our use of the environment to mimic what occurs naturally. And if we can do that, then we're working with the environment, or allowing the rest of the environment, or allowing the organic communities to maintain themselves in their natural form, as opposed to trying to regulate it. Okay, we're going to talk about, at the last, we sort of reached the bottom end of this plot, and we've moved into the tundra environment. So here, right at the north of Europe, or northern North America, and sort of in an Arctic or a subarctic environment. This area, or this environment, is characterized by extremely low temperatures and also extremely low rainfall. Slightly above sort of polar desert, but still very low rainfall. It's a very, so we talked previously, when we talked about some desert environments being low productivity. We see that again here. It's not warm enough for tree growth. A lot of the soils are permafrost, so that the soil will remain frozen throughout the year. Areas that are characterized by extreme winters, polar night, so we've got polar darkness here for 3 months of the year at least. Very, very slow growth, very low productivity zone. Any impacts, if there happens to be a fire or something like that here, very, very slow recovery. Low plant biomass, low plant diversity leads to low animal biomass and low animal diversity. As the climate is changing, and as as climate is changing, we're seeing warming. That is not predominantly, but it is unevenly distributed. The Arctic and subarctic areas are warming faster than anywhere else on the planet. And that's resulting in a contraction of this habitat as the tree line moves further and further north. As winters get shorter, trees are able to exist further and further north. It also makes these areas more hospitable to people. It's easier for people to live here. And that's resulting in an opening up, particularly in North America, an opening up of the Arctic to resource exploration, to a lot of mining. There's a lot of mining in the Arctic, mining happening in Northern Europe and Eurasia. From an ecological perspective, that's a massive risk, because it's still taking a long, long time for this environment to recover from any of that activity. So that's our sort of walk through terrestrial environments, so terrestrial biomes. From here on in, we're going to shift and talk more about, in the next section, we'll talk a bit about landscapes, and then more about sort of nutrient dynamics and how they flow through the landscape. On Wednesday, the first of the guest seminars will be Dr. Kurt Samways, who's a lecturer here in the biology department. He's going to talk about a really, really nice project he's involved in, a novel strategy to try and restore salmon populations in the Bay of Fundy. And I'll see you on Friday. All right, don't forget to vote, by the way.